pH calculations in A-level chemistry can seem never-ending, but there are some useful templates and repeating aspects of the calculations, which when spotted and rehearsed, can make the topic much more manageable. The biggest hurdle, in my opinion, is identifying the context of the calculation and knowing which setup to use before getting started. In this tutorial, I'm going to run through 21 different calculations covering the main types and styles of pH calculation we see pop up in A-level chemistry exams. Copies of the questions I'm using are available in the video description, along with timestamps, so that you can fast-track this tutorial to the types of calculation that you need the most help with. How you use this video to revise is really up to you, although I'd probably recommend downloading the questions first and have a go at them, either in stages or all at once, and then come back to this tutorial to see my guidance and to get the answers. Alright everyone, on screen now you can see my answers and some annotations which go right through all the different types of pH calculation. What I'll do each time is explain some background around the templates that I'm going to be using and following and why, and then I'll explain the answers to the questions. Don't forget to check the video description for timestamps that'll take you right through to the section of calculations that perhaps you're struggling the most with or want to find out straight away and then come back to the start for all the rest. It's entirely up to you how you use this tutorial. As you can see here, we are kicking off with strong monobasic acids. So let's have a little bit of background information here. So first off, we're talking about acids, of course. They are proton donors, and a strong monobasic acid here is going to be dissociating completely, and it's donating 1 H+ ion per molecule of the acid, and the best way I can think of describing that is by using this fake formula over here of a strong monobasic acid called HX. And you can see in the reaction equation underneath there, the HX is dissociating completely to give me H+ and X- in solution. Now that complete dissociation means that if I know the number of moles of HX, I know the number of moles of H+. And in fact, because they're in the same solution, I know that their concentrations are also going to be identical to each other. That then leads me to the pH calculation. And as it says here, this is the most important equation in this entire document. We're going to use it all the way through these calculations. And straight away here for the strong monobasic acids, I'm able to calculate their pH because all I need to do to find pH is do negative log to the base 10, but we don't need to show that bit, of the H+ ion concentration, which I've just identified for the strong monobasic acids is going to be the same as their acid concentration, very often stated by the exam question. And you can see that we've got that in the scenarios presented here for HCl, HClO3 and HNO3. So let's have a look at the answers. For the HCl in question 1, you can see my discussion just here mentions, just as I described a moment ago, the concentration of the HCl is equal to the concentration of the H+ ion, so therefore I'm using that value from the question as my H+ ion concentration, 0.03. I then do pH equals minus log of the H+ ion concentration, and I get a pH of 1.52. Check the precision requirement of your exam question. Does it want 3 significant figures? Does it want 2 decimal places like I'm going to use here for these? I don't know. Read it carefully. Always double check, never assume. If it says give it to the appropriate precision, then use the pre-existing lowest number of significant figures that have been used for other data in the exam question. So if you've got 3 numbers in an exam question which are to 2 significant figures, and you've got 1 number in the exam question that's to 3 significant figures, you're still going to give your answer to 2 significant figures because that's the lowest number of significant figures in the question. If we continue having a look through the rest of the answers, we can see that when we do, for question 2, minus log of the 1.2, we end up with a negative value. Now, first things first, the HClO3 might not initially present itself as a strong monobasic acid. You might look at that and think, well, how am I meant to know if that's strong or weak? Remember that you would get some framing by the exam question, and they would make that really clear. Also here, you'll notice we've got a negative answer for the pH. That's totally fine. It happens when you have an H+ ion concentration greater than 1. In fact, if you have an H plus ion concentration equal to 1, then you're going to get a pH of 0. And again, that's absolutely fine. For the third question, you can see we've got a fairly straightforward one there. Minus log of 0.12, just using the number for the HNO3, the nitric acid, in question 3, and I get a pH of 0.92. Now, I did mention at the start of this that this is probably the most important equation that we're going to see, but it's then followed up by this calculation where H plus equals 10 to the power of the negative pH, and this is just as an important equation actually. We're going to use this one a lot in a lot of different scenarios, but we first encounter it here with the pHs of our strong monobasic acids. So, what's the context here? Well, for our context this time, we're trying to get back to the concentrations. So we're effectively going back the other way, and that's what this is for. We've just done further up the page how to go from an H plus ion concentration to a pH. Well, here we're going from a pH back to an H plus ion concentration, and it's really useful, not just for strong monobasic acids. What I need to do is I do 10 to the power of the negative pH, even if the pH, as you can see for questions 4, 5, and 6 here, is a positive value. When we do 10 to the power of here, we've got to make sure that the pH is negative. So you'll notice that even though the pH was 0.7 in question 4, I've used minus 0.7 in my calculation in question 4 just below. You can see here for all of these, for 4, 5, and 6, 10 to the power of the negative pH gives me concentrations for all of those solutions. Remember here that yes, these would all be H plus ion concentrations based on the equation that I want you to learn, but for strong monobasic acids, that's equal to the concentration of the strong monobasic acid. So all of these are kind of doubling their role. They are the concentration of the H plus ion, and they're also the concentration of the strong monobasic acid in the solution. Moving on then to the pH of pure water. Now, there's quite a lot to say here, so we've got to make sure we take our time with this. You'll notice there's an equilibrium at the top, just up here. Water dissociates according to that equilibrium to give me an H plus and an OH minus ion. Now, to quantify that, we use this Kw expression here, which is referred to as the ionic product of water. Now, in the ionic product of water, you can see Kw, which is what the value is equal to the H plus ion concentration that we're now familiar with and we see the role of in the pH calculation, multiplied by the OH minus ion concentration. Now, for pure water, we're assuming that the only source of these two ions is from the dissociation of the water. So we're assuming that these two values of concentration equal each other. When it comes to the calculations then for the pH of pure water, remember that based on the previous calculations, my goal is to make the H plus ion the subject of any equation. What I can do to make my life a little easier here then is I can use Kw equals H plus squared rather than using this full Kw expression because I know that these two values are equal to each other based on the assumption we make about pure water. If I then rearrange, I end up with these pink highlighted equations, which, as you can see, I've said are very important here. And H plus ion concentration for a sample of pure water is equal to the square root of the Kw. Now you might think, well, surely that's the same for every sample of water then. No. Remember that Kw, which is quantifying this dissociation up here, is going to be just like any other equilibrium, and we're going to see the Kw value vary with temperature. And so Kw here in this calculation is temperature sensitive. So you've got to make sure you're working with the right value for the question you've been presented with. The value for 298 Kelvin, so the Kw for 25 degrees C, is available on your data sheet in the exam. Once you've done this rearrangement, once you've got this calculation and you have a value of the H plus ion, we then do what was on the previous page, as you can see here, negative log of that H plus ion concentration to get the pH. So let's have a look at some examples of this. You can see for question 7, we're working at 15 degrees C, and the Kw value is 4.52 times 10 to the power of negative 15. So here I've got my square root of Kw, so that's my square root of 4.52 times 10 to the power of minus 15, and that gives me a value of 6.72 times 10 to the power of negative 8. That would be moles per decimeter cubed, but I do tend to forget to put the units on this, so do apologise for that. Then what I'm going to do is take this value straight away and I'm going to do minus log of that quantity to get me the pH of the water at 15 degrees C, and it comes out as 7.2. And then for question 8, do the same sort of thing. I do square root of Kw. There's my value for the H plus ion concentration. That would actually be the H plus ion concentration of water at 298 Kelvin, 25 degrees C, because that Kw value is the one from the data sheet. And no surprises there then that it gives me the value of 7 for the pH of pure water at 25 degrees C. What you should start to notice here, and we'll just alert ourselves to this, is as the temperature is increasing, you'll notice then when we move to question 9 that the pH is decreasing of the pure water. Now, a novice to this would then say, well, what that means is the pure water is getting more acidic as the temperature rises because the pH is decreasing. But we know that absolutely isn't the case, because no matter what the temperature, if I'm working with a sample of pure water, I know that my H plus ion concentration is equal to my OH minus ion concentration. And so there's no imbalance there, there's no increased acidity at higher temperatures, so I'm not going to make that claim. Moving on to the pH of strong bases. Now, when it comes to strong bases, there's quite a lot, again, of background information here. Strong bases, straight away I think of sodium hydroxide. I can't help myself. I think of sodium hydroxide, I think of a proton acceptor, I think of it being soluble in solution, and we can see here of it completely dissociating to give me Na+, which I'm not going to lie, I'm not particularly interested in the Na+, really, and the most important bit here, the OH-. There's absolutely no presence in this dissociation of H+. And so straight away here we think, how are we going to be figuring out the pH of something that doesn't seem to have an H plus ion value or an H plus ion concentration at all? Well, we're going to use Kw once again, and you can see I've written that just here. Kw is really useful when it comes to the pH of strong bases because the Kw expression contains the H plus I need for the pH calculation and the OH minus ion concentration I have when I have my strong base. This time, these two values are not going to equal each other because this isn't a sample of pure water, so my rearrangement of making the H plus ion the subject is like, as you can see here in the yellow highlighted section. This is really important to remember as one of your templates for the pH of strong bases. Then I do the same as before, the minus log of the H plus ion concentration, and I have my pH. So the yellow highlighted sections here are my templates for the pH of strong bases. Let's move on to the calculations associated for the pH of strong bases. So you can see here I've got questions 10 and 11. Question 10 is going to be straightforward use of the templates I've discussed here in the highlighted yellow, and then question 11 is going to be a bit of a tweak on that, and I'll explain what it's all about momentarily. Question 10. Now for question 10, because the strong base dissociates completely, I can see here what I've done is quite similar to the strong monobasic acids in a way. I'm saying that as the sodium hydroxide concentration is 0.250, you can see I've mentioned that just there, that means I know the concentration of the hydroxide ion, the OH-, is also 0.250 because the sodium hydroxide dissociates completely. You can see here now I've got my first aspect of the templates that I need you to learn for this. So we've got the H plus ion concentration equals Kw divided by OH-. That's going to be the Kw for the temperature I'm currently working at, which is 298 Kelvin, divided by the 0.25, and it gives me an H plus ion concentration for sodium hydroxide, my strong base, equal to 4 times 10 to the power of minus 14. I then do minus log of that value, and I get a pH of my strong base equal to 13.4. Now for question 11, we have a group 2 hydroxide. And for the group 2 hydroxides, they are going to donate 2 OH minuses to solution per 1 molecule of the hydroxide. So what that means is down here, I'm doubling my barium hydroxide concentration to find out the OH minus ion concentration. So you can see I've done that doubling just here. And that's because they donate 2 OH minuses per 1 molecule of the hydroxide to solution. And they dissociate completely as well. We can see here then I follow the same stages. I get the H plus ion concentration by doing Kw divided by OH minus using this template from the top up here. And then that's going to give me a pH of 13.3 once I minus log my answer. You'll also notice I have this calculation for question 12, which is a little bit unusual, but it has been used by OCR themselves. And you can see here, everything looks normal until we're given a different Kw value because our strong base is at a different temperature. And because our strong base pH calculation uses Kw, and Kw is temperature dependent, I need to make sure I use the correct Kw for the temperature my strong base is being held at. So always read the exam questions for this very carefully in case they try and sneak that in. So my template is the same, nothing really changes. It's still H plus ion concentration equals Kw divided by OH minus. The OH minus ion concentration is the same as the strong base concentration given by the question. Just look how I've used here a different Kw than those we were using in the previous scenarios because I've got to match it to the one for this temperature. That means that the 0.4 mole per decimeter cubed sodium hydroxide at 15 degrees C is going to have a pH of 13.9. The final scenario I want to use here is going back in the other direction. So getting you to think about how you go from the pH of the solution right back to the preparation of that solution. Here for question 13, we can see it reads, calculate the mass of potassium hydroxide which was used to prepare a 250 centimeter cubed standard solution which has a pH of 12.52 at 298 Kelvin. And the Kw here is stated as on your data sheet, 1 times 10 to the power of negative 14. Now, first things first, if I'm being asked to calculate the mass of something in chemistry, it's very likely I'm going to use this calculation, moles times molar mass. And molar mass, if I know the formula, which I do here, potassium hydroxide, can be determined using the relative atomic mass values from the periodic table. So you can see here my molar mass is 56.1 grams per mole for the KOH. You'll also notice that in the exam question here, I have pH of 12.52. Now, there's only really one thing you can do with that. Much like there's really only one way I'm going to get the mass, there's only really one thing I can do with this 12.52. And that's use the calculation from earlier in this document, which is H plus ion concentration equals 10 to the power of the negative pH. So by doing 10 to the power of minus 12.52, I can get an H plus ion concentration for this potassium hydroxide solution equal to 3.02 times 10 to the power of minus 13. Then, look at this little rearrangement here. So this is a version of the Kw rearrangement that I was looking at before, where the H plus ion concentration is normally the subject. This time, because I'm trying to get to information about the KOH, you can see I've made the OH minus ion the subject, so it's now Kw divided by the H plus ion concentration. That's going to be equal to the concentration of the potassium hydroxide based on the information I described before, knowing that these strong bases dissociate completely. And that means that the concentration of the KOH, and again, apologies for not putting the units here, it's 0.0331 moles per decimeter cubed. I can then turn that concentration for potassium hydroxide into a number of moles of potassium hydroxide, putting me well on my way to calculate mass by doing concentration times volume. So I've got my concentration of 0.0331, and I've got my standard solution volume of 250 over 1,000, giving me a number of moles of potassium hydroxide of 8.28 times 10 to the power of negative 3. Then finally, as mentioned before, we've got mass of KOH equaling moles times molar mass. So that's going to be the mole value from here, units for that are mol, and that's going to be multiplied by 56.1, the molar mass of the potassium hydroxide, and it will either give me an answer depending on whether you rounded to 3 significant figures throughout or whether you left it on your calculator screen, equal to 0.46 grams or 0.47 grams. This sometimes happens in exam questions if, like me, they used an unusual pH value. I went with 12.52, and they will normally check this. You'll find lots of mark schemes sometimes allow this or that, because this kind of rounding can happen to 3 sig figs throughout, or by maintaining it on your calculator. My advice, always leave it as the big number on your calculator until right at the very end. Moving on to the pH of weak acids. This is where things can start to get a little tricky because we're well on our way towards buffer calculations now. Now for weak acids, they dissociate partially. So we can see here we have this equilibrium. It's still donating an H+ ion because it's still an acid, but you can see we're doing that partially now. They don't completely dissociate in aqueous solution. Now, once again, because we have some equilibrium here, we're going to use Ka to quantify this equilibrium dissociation. On the numerator, we have the H+ ion, the trademark of the acid, and it's being multiplied by the A-, which is the conjugate base of the weak acid. It's just the deprotonated weak acid structure. And then on the denominator, we've got the HA, the weak acid concentration. Now, we make some assumptions about this calculation. The first assumption we make actually isn't written on the screen, but it's about this HA just here on the denominator. In the equilibrium on the left, we did show it dissociating. Because this dissociation, though, is only very, very slight, we can assume that the concentration of the HA is unchanged from being undissociated to being at the equilibrium. The change is only ever so slight, so I don't need to adjust any values for HA concentration that I'm given by a question scenario. The other assumption we make is that the only source of H+ and A- that are relevant in the solution is from the dissociation of the HA, so we can assume that those concentrations are roughly equal to each other. Now, moving forward with the calculations, that change on the numerator that you can see here, where I have H+ squared, comes from that assumption. And so I only do this when I'm doing calculations, but it means I don't need to worry about the A- when I have a weak acid solution that isn't a buffer. And so I have this adjustment to Ka, which I then rearrange as a subject of H+, because we know we need H+ for the pH calculation, and we get this really important equation here, which is H+ ion concentration for a weak acid is equal to the square root of the Ka for that weak acid multiplied by the HA, the intact weak acid concentration, often stated in the exam question. The exam questions for weak acids are very rich. You're going to have everything from state the Ka expression, to convert it to a pKa, to compare weak acid strength, to then calculating pH. So you need to be ready for anything with the weak acids. And of course, as I mentioned a moment ago, they lead on to weak acid buffers. So let's have a look at these questions, and you can see for each one of these weak acids for 14 and 15, I've asked you to write the expressions for Ka, convert the Ka values to pKa, and then calculate the pH values of the solutions. And I'm using here one acid that OCR have used quite a bit recently, which is nitrous acid. That's the HNO2. And I'm using one they haven't used very often at all, which is the iodoethanoic acid, CH2ICOOH. Now, the reason I'm using these, the HNO2 is a bit like nitric acid, so there's a temptation to write HNO3 instead of HNO2. And the iodoethanoic acid, it's very tempting to write CH3 in this instead of CH2I. And again, these little attention to detail will help you when it's revision time. So for question 14, first off, I'm writing the Ka expression, very common question in the exam. Notice how I haven't done the squared aspect on the numerator here because I'm writing it out for the first time and I don't want to make that approximation. You'll also notice then for part 2, I've calculated something called the pKa. The pKa scale is just a simplification of the Ka scale, and it just changes it in the same way that we convert an H+ ion concentration to a pH. So negative log of a Ka gives you a pKa, and the greater the Ka value, then the smaller the pKa. If you'd like to compare pKa values of different weak acids, there's a video that you can click at the top of the screen now, and I'll put it in the end screen as well for this tutorial. So, moving on to part 3, the pH of that nitrous acid solution. You'll see I've got my use of the template just here, really important. H+ ion concentration for a weak acid equals the square root of the Ka multiplied by the weak acid concentration, just there. I've put the numbers in, so you can see exactly which numbers I've used from the question there, and I get an H+ ion concentration here equal to 4.78 times 10 to the power of -3. When I minus log that quantity, I get a pH that you can see here of 2.3. There we go. For question 15, I've done exactly the same kind of thing. I've written out the Ka expression really carefully to make sure I don't accidentally write CH3. I've calculated the pKa by doing minus log of the Ka, and then I've calculated the pH of the solution, which comes out as 1.6. That leads us on to buffer calculations, weak acid buffer calculations, in fact, which I think people have a little bit of a vendetta against. They're not that bad in my opinion. As soon as you realize how they are different from a regular weak acid calculation, I don't think they're that bad. I suppose the fear here is there's more scenarios they can play with in the exam when it comes to weak acid buffers. But I'm going to take you through lots of different scenarios here, so that should really build your confidence for it. So, first off, what's the same? It's still Ka. It's a weak acid, so I'm still going to have to use the Ka expression to find that H+ ion concentration that I'm going to need for the pH calculation. So I'm still using Ka here. That isn't going to change. What is changing? Well, beforehand, we were looking at how the numerator here, the H+ ion concentration and the A- ion concentration for a weak acid solution were basically the same as each other, so we could just square the H+ ion concentration on the numerator and rearrange from that point. Now we have a separate source using a sodium salt of the weak acid, so the A- value is actually greater than the H+, and so I can't use that squared feature at the top. So I just have to treat the A- as its own quantity, and the question will provide me with information about that. Or I suppose they might ask you to calculate that value. That could be the goal of the question. The other approximation that we made about the HA being the same undissociated as it is at equilibrium in terms of concentration still stands. So I still don't need to change the denominator value here for the HA concentration, the weak acid concentration, despite the fact it's dissociating, because that dissociation is only slight. The major thing here is making sure I don't use that squared feature before for the H+ ion concentration, since the values on the numerator here are no longer very similar, or the same. So, what are my very important buffer equations? Here they are. My rearrangement of H+ is now a little different. The H+ ion concentration now equals, sort of same as before here, Ka multiplied by HA, it's just what we were doing before was square rooting that, except now there's no square root and I'm dividing by the A- ion concentration on the denominator. Once I have the H+, then nothing changes from that point. I'm going to do minus log of the H+ ion concentration, just as I've been doing previously. Let's have a look at all of these scenarios and make some sense of what's going on here. First off, calculate the pH of a buffer solution which contained 0.5 mol per decimeter cubed of propanoic acid and 1 mol per decimeter cubed sodium propanoate. Now here you can see I've got my Ka expression in the answer space and I'm labeling up the values I have. So my sodium propanoate is providing me with this A- value here, the propanoate ion, and the propanoic acid is actually shown in full on the denominator just here. So I rearrange, so you can see here this rearrangement is that part of the templates on the top, and I've popped the numbers in. Please notice here what I'm actually using are the concentrations from the question. But if I was actually given moles instead of concentrations and I didn't know the total solution volume, I can actually just use moles. And that's okay. I'm allowed to use moles in this calculation rather than concentrations, because if we have a peek at the general template just here, the HA and the A- are in the same solution. So the volume term within both of those concentration terms, because concentration equals moles over volume, the volume terms there are going to cancel out. And so I can just use their correct mole values for the buffer solution. That's absolutely fine, and I'll demonstrate the use of that shortly on the page, because it can speed you up in the exam. Now you can see here, once I've done my rearrangement, I get my H plus ion concentration from calculation, and it's 6.75 times 10 to the power of minus 6 moles per decimeter cubed, minus log that value, and the pH of this buffer for question 16 is just 5.2. What some people do is they make the mistake of assuming that the sodium propanoate and the propanoic acid are actually going to react with each other and the moles are going to be adjusted, but that isn't the case. They don't react with each other, they're just both part of that weak acid dissociation equilibrium, and so we need to represent them separately in that rearranged Ka. Question 17. Calculate the pH of the buffer solution, which contains some masses of ethanoic acid and sodium methanoate. Now here you have actually been told that the total solution volume is 100 centimeters cubed, but what I want to demonstrate with this one is, even though I'm going to write that they are concentration terms in my rearrangement, and that's for the ethanoic acid and the sodium methanoate, I'm actually only going to use their mole values, and you can double check this, maybe convert them into concentrations, or you may have already done. You will end up with the same value of pH at the end here. So what do I need to do to begin with? Well, I need to figure out the mole values of the ethanoic acid and the sodium methanoate. I can then convert that into concentrations if I want, but moles is the top priority. So for each of them, I've got masses. There's only really one thing I can do with that. Mass divided by molar mass is going to give me moles. So for the ethanoic acid, the mole value is 0.2, using a molar mass of 60. And for the sodium ethanoate, the molar mass value there is going to be 82, giving me a mole value of 0.05. Putting that into the rearranged Ka expression, which is part of my templates that I need to learn to make sure that I have the H plus ion concentration easy to calculate for the buffer. It gives me a value of 6.96 times 10 to the power of minus 5, and that gives me a pH of 4.2. Question 18. In what proportions, now this is a ratio question, very common for buffers, should you mix 1 mole per decimeter cube solutions of methanoic acid and sodium methanoate to give a buffer solution with a pH of 3.50? All right, first things first, we've got a pH. We know what to do with it. 10 to the power of the minus pH gives me the H plus ion concentration. Now I've been asked here for two quantities from the Ka expression. I've been asked for the sodium methanoate, which is represented by the methanoate ion in the Ka expression, and I've got the methanoic acid. Now, this is quite common. You can see my rearrangement here is a little bit unusual, but it's just writing out and knowing the Ka expression. And I've got my two terms that I have values for here, and you can see the values just alongside it. And if I do this calculation, if I do the 1.78 times 10 to the power of minus 4 divided by the 3.16 times 10 to the power of minus 4, that's going to be a value that I can associate to these two in a ratio. So on the calculator, it actually comes out as 0.563. All I need to do is write that over 1, and that's telling me the ratio that these two need to be in order to create a buffer solution with a pH of 3.50. Very often in the exam, they give you a line like this one, and they ask you to put the numbers above and below. The most difficult kind of buffer calculation they can give you is that in order to achieve that scenario of a weak acid and its sodium salt in the same solution, rather than actually adding the sodium salt directly to the weak acid, what they might do is add an excess of the weak acid to a limited amount of strong base. The strong base reacts completely, producing some sodium salt of the weak acid. You have your weak acid left over because it was in excess, and you've got your buffer solution that way. For that kind of scenario, you need to be aware that the sodium hydroxide or the potassium hydroxide, whatever, is going to react with the weak acid. So you need to figure out the ratio that they're going to react in. Here I'm using a ratio of 1:1. You need to work out how many moles of the weak acid are in excess. You also then need to work out how many moles of the conjugate base of the weak acid, the sodium salt of that weak acid, we can call it, have been formed, and then you put them into the rearranged Ka expression that I showed you on the previous page. So let's have a look. Well, I've got the reaction equation just here, so I've got my benzoic acid reacting with sodium hydroxide, and they react in a 1-to-1 ratio. So I've calculated my moles of benzoic acid as 0.01, and I've got my moles of the sodium hydroxide as 1 times 10 to the power of minus 3. Now you can see here the difference between these two numbers is going to be the number of moles of HA that are going to be remaining behind in excess, and that's equal to 9 times 10 to the power of minus 3, and that's the moles of benzoic acid left unreacted. All of the sodium hydroxide has gone. I've also produced in this reaction some moles of the A minus because that's the product when the acid and the strong base react together. Now this value and this one here, so that's for the HA and the A minus, can be at this point converted into concentrations by dividing by the final solution volume, which in this case, if we consider we had 100 centimeters cubed of the benzoic acid and 10 centimeters cubed of the sodium hydroxide, is going to be 110 centimeters cubed, over 1,000 for the calculation. But remember, I don't need to do that here, and what I can do to save some time is just put the mole values for these in instead. So this isn't a mistake, it's just a little bit of a shortcut, and you actually find this is used very often in exam mark schemes, and you don't often get much credit, if any, for converting into concentrations at this point because it's not required. That gives me an H plus ion concentration equal to 5.68 times 10 to the power of minus 4, giving me a pH of 3.2 when I minus log that quantity. This is the final page of these pH calculations, and what we're looking at here is a nice follow-on from the previous section, and it's all about the pH of a final solution or a resulting solution. What very often happens is similar to that final buffer scenario. They give you a strong acid and a strong base. They react in a 1-to-1 ratio or something very close to that, and they give you moles of each of them by using concentrations and volumes, and one of them is in excess. The resulting solution then is going to be a mix of salt water and whatever component, either acid or base, that was in excess, and then you're going to use those excess moles to figure out a new concentration of that component and then the resulting pH of that solution. So let's have a look at this scenario for question 20. In question 20, if you work out the number of moles of HCl, you find that it's 0.0375 from the information in the question, and the potassium hydroxide is 0.0240. Now, the HCl there is in excess, because if I look at the difference between these two numbers, it comes out as 0.0135 mol. Now, that mole of HCl in excess needs converting into a concentration, because as we learnt on the very first page of this, if I can find the concentration of the HCl, that's going to be identical to the concentration of the H plus ion, which you can see I've done here using the new solution volume, that final solution volume of 115 centimeters cubed converted into decimeters cubed for this calculation. So the concentration of the H plus ion in this solution after the reaction is 0.1174 mole per decimeter cubed. Minus log it, and that gives me a pH of the final solution of 0.93 at this point. What if I reverse the roles? Well, in the next scenario for question 21, hopefully what you notice here is I've got the same data as the previous question, it's just I've swapped round the roles here. So I've swapped round the acid for an alkali and the alkali for an acid. So this time I've got nitric acid, strong monobasic acid, strong base of sodium hydroxide, and using the same data but the other way around, it's now the sodium hydroxide that's in excess. So I turn that number of mole value here into a concentration of sodium hydroxide, and I end up with the same concentration as the HCl in question 20. But here's where things change a little bit. Now that it's the alkali, the strong base here in excess, you can see I've got my OH minus ion concentration here instead of an H plus ion concentration at this point. That means I need to use my rearrangement of Kw, which we haven't seen for a couple of pages now. It's H plus ion concentration equals Kw divided by OH minus ion concentration. And it gives me a value for the H plus ion concentration of 8.52 times 10 to the power of minus 14. Minus log that value, and here I get a pH of 13.1. So it's all about finding which one is in excess when the mixture is being formed, and then knowing to turn that number of excess moles into a concentration using the new solution volume, and then knowing what to do with that concentration. If it's a strong monobasic acid, just minus log it. If it's a strong base, you're going to need to use the rearrangement of Kw, as you can see on screen. It's about being flexible and aware of the different types of formulae. It's really important to know your formula in A-level chemistry, and this is a classic example of why. I hope you found this coverage of the pH calculations very informative. If you check the video description, you will also find right at the bottom after the timestamps that there is actually a link to this filled in version. So if you want all of the answers as well as the blank set of questions, you're more than welcome to click the link there and get access to all of those. Thank you very much for watching. If you found the video helpful, I would really appreciate it if you could give it a like before you go and consider subscribing to stay updated. But until next time, happy revising.